We're in chapter 6 here. So what we're going to do is actually we're going to start here a little bit ahead of where we left off last time with chemical bonding in the notes. Those that had discussion on Monday, we finished up sort of the nomenclature part of it. And those that have discussion today, we'll go over the nomenclature part with you today during discussion. And then everybody will hopefully be at the same point. So with everybody here together, we're going to pick up in our notes on chemical bonding. And again, like I said, if you're here on Monday discussion, you already got the rest of the nomenclature. And if you have discussion tonight, you'll have the rest of the nomenclature tonight. Okay, so we're going to talk about actual chemical bonding. And we talked a little bit about really the two different types of bonds that we do commonly come across. And as we talked about when we talked about nomenclature, there really is the Ionic bond, which is between a metal and a non-metal, and we do get the transfer of electrons that occurs in that situation. We also have, excuse me, the covalent bond, which is between two non-metals, and we have sharing of electrons that are going to occur there. Again, as we talked about, basically, we'll get that sharing of electrons in a covalent compound because pretty much non-metals have the same periodic trends. They both pretty much want to hang on to their electrons. So the best that they do is basically sharing those electrons. And as we'll talk about, maybe shared equally, maybe shared unequally, but there's some aspect of sharing that occurs when two non-metals come together. And that's very different than what happens when metals and non-metals come together. When metals and non-metals come together, basically metals have properties of, I really would like to give away my electrons. Non-metals basically have properties of, I like to take your electrons. So what we end up getting in an ionic compound and in an ionic bond is we actually get a complete transfer of electrons from the metal to the non-metal. The result of that is we will end up with the metal becoming positively charged and the non-metal becoming negatively charged. And there's absolutely no sharing of electrons in an ionic bond. Is that positive negative attraction or electrostatic attraction, which is really what holds sort of the ionic bond together. Now, regardless of the type of bonding, we oftentimes will use Lewis dot symbols. Again, they are also sometimes referred to as electron dot symbols. Basically to illustrate the types of bonding, because really bonding only involves the valence electrons, which are our outermost electrons. We only show basically the valence electrons in this, and I think we looked at it earlier, but again, basically we do no more than 2 dots per side with the symbol. And that's typically how we draw our Lewis dot symbols when we are talking about bonding. Also a reminder that the valence electrons are those outermost electrons. They are equal to the group number is the much faster way of figuring out how many valence electrons everybody has. So you just want to look at the actual group number there to get what you need. All right, so I think we looked at this a little bit earlier in our chapter, but if not, let's just take a look at it again. These are electron dot symbols, our electron dot symbols. For each of them, everybody in group 1, as you can see here, has 1 valence electron to all the way to group 8. Also, just a reminder again, although helium is part of group 8, it only has 2 total electrons. Its electron configuration is 1s2, which means both of those are the valence electrons. But everybody else in group 8 will need 8 valence electrons as you go down. The roll is coming from the top down this time, yeah? So let's first talk about the different types of bonding that we see. First off, as I just mentioned, our ionic bond, as we talked about with naming, is our metal and non-metal. Again, here we're going to see that transfer of electrons over from the metal to the non-metal. That's going to result in a cation being formed from the metal and our anion from our non-metal. And again, absolutely, the important thing to keep in mind here is there are no sharing of electrons. It is that negative and positive attraction that holds that together. And again, that is very different than when we're dealing with our covalent compounds. Those are usually with 2 nonmetals. And again, here, the major difference is, as I said just a second ago, we are going to have some sharing of electrons that are basically going to occur. Talking about some of those periodic trends that we talked about last time, things with very low ionization energy will tend to form cations. They're positively charged. Again, ionization energy is the energy required to remove an electron from an atom. So those with low ionization energy means it doesn't take a lot to convince them to sort of give away their electrons or give up their electrons. Those that have high electron affinities tend to form anions. Electron affinity is basically the energy change, again, that occurs when somebody gains an electron. And that typically on the periodic table increases as you go up and to the right on the periodic table. And that's basically where we find our nonmetals. So as we talked about, that's really what happens between those two types of elements. Metals, because of their properties, will give away electrons. Nonmetals will pretty much try to accept electrons. And it really creates the basis for the different types of bonding that we see. So general rule tells us that obviously our metals on the left there, especially in group 1 and group 2, will give away electrons. And our oxygen, the halogens, which is the main chunk of our nonmetals, will typically be those guys that will gain electrons. So let's actually take a look at an example here of lithium fluoride. So if we look at lithium, the electron configuration is 1s2, 2s2, and 1s2, 2s1. And if we look at fluorine, the electron configuration is 1s2, 2s2, 2p5. So we have basically a metal and a nonmetal here. So as soon as you sort of see that combination of those two things, it should automatically scream to you that this is an ionic bond. We're not going to have any sharing of electrons here, but we are going to have a transfer of electrons from our metal to our nonmetal. So if we were to draw our sort of dot structures for this, lithium, which is group 1 on the periodic table, should have 1 dot there. Again, if we write its configuration 1s2, 2s1, and we take our fluorine here, which is group 7 on the periodic table, should have 7 dots around it, with its 1s2, 2s2, 2p5. So again, in this situation, because we have our metal and our nonmetal happening here, we are going to see lithium pretty much give up its electron over to the fluorine. The result of that is the lithium will have now lost an electron, and it's at this point that it will become positively 1 charged because it lost the electron. On the other hand, our fluorine will say thank you very much and pick up that electron. As a result of that as well, the fluorine picks up that electron and now becomes negatively charged. And it is that attraction between the positive and negative charge there that holds that together. And that is why in an ionic compound, where we're drawing these sort of Lewis structures, if you will, we should always include the charges to indicate that there are no electrons being shared between them. And in a lot of cases, people will put brackets, at least around one of them, like the negative guy here. Sometimes people will put brackets around everybody, but you should definitely include the charges here when you are drawing something that is ionic, like we have here. So what is really happening here is, I think, what we might have mentioned before, but just to make sure everybody understands, the goal of pretty much all bonding is, again, for everybody to achieve the same electron configuration as the noble gases. So if we look at what's really happening here with lithium, lithium pretty much just gave away this valence electron right here. When it does so, lithium with a +1 charge ends up with an electron configuration of 1s2. Now, the fluorine has some room there in the p orbitals, right, to accept that 1 electron that came over. When it accepts that 1 electron, the fluorine ends up with 1s2, 2s2, 2p6. If we look at where they ended up, both of these guys, lithium ended up with 2 electrons, which is the same thing as helium on the periodic table. And fluorine, by accepting that electron, ends up with 10 electrons, which is the same thing as neon. Remember, when two things have the same electron configuration, they are rather referred to as being isoelectronic with each other. And what they essentially have done is they have now made themselves very much like a noble gas in terms of electrons. Again, a reminder here, it is just the electrons that did that. we did not change the protons or anything like that, because obviously we would change the element, but by getting themselves into that same sort of electron configuration as a noble gas creates really a basic and stable arrangement for them to come together. And that, for all the craziness of bonding, that is really the goal there, is for everybody to end up with basically the same electron configuration as those guys in the noble gases. Noble gases are chemically inert. They are extremely stable sort of situation. And that is really the goal here. How metals and nonmetals achieve that in ionic bond is metals will lose electrons. And if you look on the periodic table, it will back up to the noble gas that comes right before it. And nonmetals will accept the electrons. And if you look on the periodic table, they will go forward to the noble gas that comes right after them. So if you look on the periodic table, you see helium that comes right before lithium, and you should see neon that comes right after fluorine there. Any questions on that there? So again, that is the basis of an ionic bond. As I mentioned a bunch of times, no sharing of electrons here. It is what is referred to as electrostatic attraction. Again, that positive and negative attraction. It actually does increase with strength, actually with the size of the charges. So things like +3 and -3 are actually held together a lot stronger than something that's +1 and -1. It's a super, super strong attractive force, the electrostatic attraction. It is so strong. It's why when we take, if you took something like sodium chloride salt and you heated the heck out of it, it will never break apart into gas. It will just start melting. That's how strong that attractive force is. It's pretty much one of the strongest sort of attractive forces you could have, is that positive negative attraction that basically occurs. Let's take a look maybe at another example here, which is calcium oxide. So that's calcium and oxygen coming together. So if we look at calcium, which is group number 2, we know that it should have 2 valence electrons in this case. And if we were to write the electron configuration, it is 20. So it's 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2, if I squeezed all that in there. At this point, we are then going to add it to our good friend oxygen, which is group 6, which means it gets 6 valence electrons. It also has an electron configuration of 1s2, 2s2, 2p4. In this case, we have calcium here that is going to take an electron, and it's going to give it up over here to oxygen. Now, let's just say, for example, calcium has 2 valence electrons, right? Because it is group number 2. If it only gives away 1 electron, is it happy? It is not, because if you just simply look at the periodic table, if it only loses 1 electron, it backs up to potassium, which is a great element, but really not a noble gas. So the calcium here does want to give away 2 electrons, which is okay in this case, because really the oxygen kind of wants 2 electrons anyway in this case. So the second electron is going to come on over here to our oxygen. The result of that is our calcium has now lost both of its valence electrons. It will end up with a +2 charge to reflect that it lost both electrons. The oxygen there will pick up both of those electrons, and that's going to get our oxygen to now gain a -2 charge and basically 8 electrons around it. Same sort of situation occurred here. If we look at calcium, it laid up its 2 valence electrons right there. That leaves calcium with 18 electrons. And if we look on the periodic table, lucky number 18 is argon, right? And that allowed calcium to achieve argon's electron configuration, which is really the goal. Oxygen, again, has a couple of spaces right there in its p subshell to take those 2 electrons. It will take both of those electrons and bump really oxygen up now to 10 total electrons. And that will then move oxygen forward to neon's configuration. So again, here by transferring electrons in an ionic compound, our metal again was able to back up to the noble gas that came before it and get that good noble gas configuration. Our oxygen was able to go forward and achieve that noble gas configuration of neon. Any questions on that there? Again, this is again an ionic compound, and you simply know that by it's a metal and non-metal. That's pretty much all you need to worry about. That tells you it's ionic. So again, when you draw these, there should be charges, and obviously to indicate that there's no sharing of electrons. Any questions on either of those there? Now, let's put together, for example, two of our good friends there that we just saw. Let's take calcium in this case, with again its configuration of basically argon 4s2. And let's actually put it together with fluorine that we saw earlier, which has its 7 valence electrons, and its configuration of 1s2, 2s2, 2p5. So the same thing is going to happen in this case. We're going to get our calcium wanting to give away its electrons. So calcium is going to take an electron and send it on over to fluorine. At this point, what happens to our fluorine? Can it take any more electrons? It cannot. And calcium, as we just talked about, is not super happy with only giving up 1 electron, right? So in this case, to sort of make sure everybody's happy, not just fluorine, we actually would need 1 more fluorine here to take that 2nd electron in this particular case. And the result of this is we actually will end up with a calcium again that will hit the +2 mark as it loses 2 electrons. We will end up with 1 fluorine that picked up just 1 electron, which means it became negatively 1 charge. And we will end up with a 2nd fluorine that also picked up 1 electron and became negatively charged. At this point, calcium has now achieved argon's configuration by giving away the 2 electrons. Each of the fluorines individually have each gained 1 electron, which would move each of the fluorines to 10. And each of the fluorines have now gained neon's configuration. All 3 of those guys are very happy at this point. They've all been able to achieve noble gas configuration. Perhaps you remember when we were talking about naming, when we put together an ionic compound, something with a charge, and we put it together, the overall charge should equal what number? Should equal 0 when we put together ions, right? So if we were going to put these guys together, that's why we were talking about earlier that you need 2 of these, right, to balance it out, and you get the proper formula CaF2. The real reason for that is you need it to get everybody to the noble gas configuration. So the real reason why we sort of balance out the charge when we in an ionic compound, when we take a positive guy and a negative guy together in the simplest way possible to do that, is when we do that and we balance out the charge to 0, we're essentially allowing all those guys to achieve noble gas configuration. It's really the bonding aspect as to why we put it together like that. Any questions on that there? Questions on ionic bonding here. So this is how we could use Lewis dot symbols to help us illustrate ionic bonding. A little bit different with covalent bonding, which we'll talk about in just a bit here. All right. So let's get into actually covalent bonding. So covalent bonding, as I mentioned before, occurs when we have really 2, those dots are crazily wrong in the wrong spots. All right, we'll do a little adjustment of this here. So the covalent bond is what happens again when we have 2 nonmetals. And it is this sharing of electrons. And as we'll talk about here in just a second, maybe equal sharing or unequal sharing of electrons. So I'll just redraw this whole thing. So if we have our hydrogen here that has 1 electron, and we put it together with another hydrogen here that has 1 electron. In this particular case, they're both nonmetals and they're both hydrogen, which means they have the exact same periodic trends, which means neither one of them wants to give up its electron. So what's going to end up happening is instead of transferring electrons, we're actually going to get those electrons to be shared between the 2 nonmetals. The result is you could represent that with 2 dots in the middle here of both hydrogens. And when we look at the dots in the middle are the electrons that are being shared, The 2 electrons count for the guy on the left, and the 2 electrons count for the guy on the right. And by sharing electrons here, each of the hydrogens are able to hit 2 electrons. You could also represent this with a line. One line represents a pair of electrons or 2 dots. That's a single bond. Double bond, as we'll see, is basically 2 lines that represent 4 dots, and a triple bond is 3 lines that represent 6 dots. So this is a covalent bond. Those electrons are basically, because they're negatively charged, they're attracted to like the positive nucleus on the guy on the left, but they're also attracted to the positive nucleus on the guy on the right. So that sort of dual attraction kind of locks those electrons in between the 2 atoms, and that's what basically makes a covalent bond. 2 electrons is important for hydrogen because who is number 2 on the periodic table? It is helium. And this is a very important thing to remember, that hydrogen only needs 2 electrons, because if you look at the periodic table, that is enough to get hydrogen to helium, which is a noble gas. So it should only be 2 electrons. Hydrogen should pretty much only look like that. You should never have hydrogen in the middle. You should never, ever, ever put dots around hydrogen, because that's just going to give you like an X. Yes, so that is definitely wrong. So never have dots around it. By the way, you should never double bond, triple bond hydrogen, because that'll get you another X. Yeah, so don't do any of those things. Hydrogen is pretty straightforward. It's like a line that represents 2 electrons, and that's it on the outside. So if you find yourself doing any of those things, put the X yourself. Save me a trip. Yes. All right. So in a covalent bond, as I mentioned, because those negatively charged electrons, they're basically attracted to each of the nucleuses. That is really what holds that together. And as we'll talk about here in just a bit, you know, the electrons may be shared equally like it is in hydrogen. In hydrogen, we would expect it to be shared equally because they're both hydrogen. So if you think about the pull on the electrons, they're both going to kind of pull those electrons equally because they're both kind of like the same guy. And that is what is referred to as a covalent bond. Now, if we take a look at F2, for example, F2 here, fluorine has 7 valence electrons. So again, in this case, they are both fluorine. They are going to end up sharing those pair of electrons there. And again, you could represent it one of 2 ways. You could represent it as dots, like we see here, are the electrons, which are referred to as bonding electrons between 2 atoms. You could refer to or draw them as a line. And when we sort of look at this guy drawn together, if we kind of look at the fluorine on the left, taking those 2 in the center, it ends up with 8 electrons. The fluorine on the right, they're also sharing those electrons in the center, will end up with 8 electrons. 8 is a super important number here in bonding. 8, as we'll see in just a sec, is what is referred to as the octet rule. It is really the goal, what everybody's trying to achieve. And that is because 8 puts us where on the periodic table? Right there at the noble gases, right? So how covalent bonds work, or nonmetals work to kind of get themselves to that noble gas configuration, is because really neither one of them want to transfer their electrons. They decide we will share electrons, and by sharing electrons, that allows everybody in a covalent bond to move themselves to the noble gas configuration like we see in an ionic bond without the need of transferring the electrons. That's also why we don't get a full charge that occurs here. There's no positive or negative that sort of occurs fully with a covalent bond. Any questions on that there? Okay. Now, there's 2 different types of electrons that we do see when we draw a picture like this. They are what are referred to as non-bonding electrons. Non-bonding electrons are, if you're old like me, lone pairs. Nah, people still use it occasionally. Not so much anymore, but you know. All right, so all these guys that are obviously dots when you draw your Lewis structure here, and there's no other element or atom on the other side of those dots, are what are referred to as lone pairs or non-bonding electrons. So again, if I say lone pairs, the same thing as non-bonding electrons. The other type of electrons that we got going on there are actually the electrons right there that are involved in bonding. And they also have a very fancy name known as bonding electrons. Yes. So much like the name implies, bonding electrons are electrons that are involved in an actual bond. Non-bonding electrons or lone pairs are ones that are not involved in bonding. You should always, when you draw Lewis structures, include all those electrons, both the bonding and the non-bonding, in your picture. Also, it's important to remember that as we use Lewis structures or symbols here to represent covalent bonding, we are only really looking at valence electrons. Everybody still has more electrons. I think we talked about it when we looked at, say, something like 1s2, 2s2, 2p5 for fluorine. These right here are the valence electrons. And these guys, which are lower in energy, are what are referred to as core electrons. And those are the guys much, much closer to the nucleus, I think, as we may have talked about last time. And because they're so much closer to the nucleus, they're held a lot tighter. So they really don't participate in bonding. It is really only the valence electrons, those outer ones that are, again, further away from the nucleus, not held as tightly. And really the ones when two atoms come together actually come into contact with each other. So those are really the ones involved in bonding, just the valence electrons. So we take a look at another example. If we draw water here in this particular case, by actually sharing electrons, the oxygen with the hydrogens will allow the oxygen in the middle there to achieve 8 electrons, which makes it really happy. As we can see with our hydrogens, as we talked about before, and on the bottom, by sharing with the oxygen, it's able to achieve 2, which is exactly what hydrogen needs. So again, here by sharing electrons, our hydrogen is able to get himself to 2. Our oxygen is able to get itself to 8. Now, in certain cases, you can get everybody to the octet rule and happy with 8 by just doing single bonds. As we'll talk about, in some cases, you may actually need to make some double bonds to get everybody to sort of 8. And in some cases, you may actually have to triple bond to sort of get everybody to 8. But the goal is when you're all done with your sort of structure there, everybody should have 8 except for hydrogen, which obviously is, as we've talked about here, basically what the octet rule is. The octet rule is pretty much everybody except for hydrogen will continue to make bonds until they get themselves to that magic 8 number. Hydrogen, again, as I said, only needs to get itself to helium, and that is sometimes referred to as the duet rule. We will talk a little bit about some exceptions to the octet rule, but in this class, we will have no exceptions. Everything that we do in this class will follow the octet rule. In real life, there are some exceptions, obviously, to it, and we'll talk about a few of those towards the end. But anything that you draw in terms of covalent bonding and Lewis structure should always obey the octet rule in this particular class. Yeah. Any questions on that there? So we talked a second ago about single bonds. So let's talk about some other ones. When we do have a single bond, that again is the sharing of a pair of electrons between 2 atoms. So a pair of electrons would be 2 total electrons. And as I mentioned before, you could represent those bonding electrons with a line, 1 line, or you could do 2 dots. Personally, and most people will usually use lines to represent the bonding electrons and obviously dots to represent the non-bonding electrons. But technically speaking, you could do dots on everybody if you want, bonding electrons as well. But most people will sort of use the line for the bonding electrons. Again, as I mentioned before, sometimes things do need double bonds to get themselves to the octet rule. CO2 is an example of that. The carbon actually has to make not 1, but actually 2 double bonds to get itself to 8 electrons, 1 on each side. And that's what we see here. It's able to get to 8. Each of the oxygens as well, if you count up all the oxygens in the circle there, also gets themselves to 8 and makes it really happy. Obviously, a double bond is 2 lines are 4 total electrons or 2 pairs of electrons that are there. And sometimes, as I mentioned earlier, it does take a triple bond to get yourself there. And here's a couple of examples of triple bonds. Nitrogen, for example, each of the nitrogens will never get themselves to 8 unless they triple bond up. So nitrogen does need to do the triple bond. That is the sharing, as we can see here, of 6 total electrons. And each of the nitrogens are able to get themselves to 8. Again, a triple bond represented by 3 lines are a total of 6 electrons. By the way, you should kind of stack your electrons. If you are using dots, especially for bonding electrons, you should not show a triple bond like this. That's just a lot of dots in a row. Yeah, so don't do it like that. So you should do some type of stacking situation there when you are doing some type of triple bond. On the bottom here, we actually see a carbon needing to make a triple bond with another carbon to get itself to 8. And again, we again see, can't say it enough, people always screw up hydrogen. Only 2 there for hydrogen. It's all it should have. Again, in most cases, that's exactly how hydrogen should look, a line to an H, and that is all you should put there. Any questions on any of that there? So let's talk a little bit about electronegativity. Electronegativity really is, what helps us decide our electrons. Well, it can't help us decide if electrons are going to be shared. But mostly we will use electronegativity to help us decide, are the electrons going to be shared equally or are they going to be shared unequally? Electronegativity, I think we talked about a little bit when we were talking about sort of those periodic trends. Electronegativity is the ability of an atom to bring electrons towards itself. I think we'll see it here in just a sec, but a reminder that it increases on the periodic table as you go up and to the right, fluorine being the most electronegative, decreases as you go down and to the left on the periodic table. It is really what helps us decide, what type of sharing we're going to actually occur. So for example, if we had something like H2 that we saw earlier, we would expect that those electrons between the 2 hydrogens would really be shared pretty equally. Again, you could think of it like kind of pulling on a rope, if you will. Both hydrogens are going to pull those electrons equally, the same amount, because they're basically the same element. So really bad drawing here, if my lines are the electron sharing, you have sort of equal sharing of those electrons between the 2 hydrogens. In a case where we have equal sharing of electrons, that is what is referred to as a nonpolar covalent bond. Most people really shorten it to just a straight nonpolar bond. It's assumed to be covalent. So a nonpolar bond arises when you have 2 atoms that are sharing electrons equally between them. The result of that sharing of those electrons equally between them basically results in overall like a neutral bond, if you want to think about it that way. There's like no side that's more negative. There's no side that's more positive. There's just a nice equal sharing overall of those negatively charged electrons in a nonpolar bond. You will always get a nonpolar bond if you have obviously 2 elements that are exactly the same sharing the electrons in a bond. That's a for sure nonpolar bond situation. So the F2 that we saw earlier would definitely be a nonpolar bond as well. Again, both of those guys would be pulling those electrons equally to each other. Now, what happens though if we kind of switch out and put like a hydrogen with a fluorine? Now, when we put the hydrogen with the fluorine, between hydrogen and fluorine, the more electronegative element would be the fluorine, since it is the most you could have. And what will end up happening is we will actually get a lot more of the electrons coming towards the fluorine side. Again, if my wonderful artist drawing of lines represents the electrons hanging out over there. The result of that is we're going to really get some unequal sharing that's going to occur here between the hydrogen and the fluorine. And what happens in this bond when the electrons sort of head towards the fluorine? The fluorine now becomes more positive or more negative? It should become more negative, right? Electrons are negatively charged. So as they move towards the fluorine, What we see develop on the fluorine is what's referred to as a partial negative charge. That's a delta negative symbol. That's a partial negative charge. Now, because the electrons are moving away from the hydrogen becomes sort of electron deficient, and it becomes actually a little bit more positive in that case. And it creates what is sometimes referred to as a partially positive charge in this case. You could also represent this with what is sometimes referred to as a dipole arrow. That looks something like that. The pointy part of the arrow always points to the side that's more negative. The part of the arrow on the back that kind of makes like a plus sign is to the side that's more positive. So this side is like more positive. This type of situation where we get these unequal sharing of electrons is what is known as a polar covalent bond, or just a polar bond, most people will call it. See how bad I scribbled all over that? I did. I scribbled all over that very badly. I guess I should have went low on that drawing there. But that's basically what we said here. So a polar covalent bond or a polar bond is a result of unequal sharing of electrons. The result of the unequal sharing of electrons results in actually some charges being developed here. A partially negative charge on the side that the electrons are going towards, and a partially negative side, partially positive side where the electrons are moving away from. Why are they, when we look at this, only partially positive and partially negative? Why are they not fully negatively charged and fully positively charged? Any ideas? The answer is they are still actually sharing the electrons here. So the electrons have not fully transferred from the hydrogen to the fluorine in this case. There is some aspect of sharing here. So we don't get a full positive charge, full negative charge like we see in an ionic compound, because in an ionic compound, we get a complete transfer of electrons from one to the next. Here, the hydrogen is still hanging on, not very much, but he's hanging on a little bit to those electrons. So in this case, we get what are referred to as partially positive charges, partially negative charges, because they are still technically being shared here in this covalent bond. There hasn't been a full transfer of electrons like we see in an ionic compound. Any questions on that there? All right, there's my bad smear. Look kind of like what I scribbled, I suppose. So again, these arrows you will commonly see, and they're what are sometimes referred to as bond dipole arrows. And we can use them in two ways, but this is the common way that we use it. We use it to indicate bond polarity. So there's two types of polarity we're going to talk about: molecular polarity and bond polarity. What we're talking about now with electronegativity is what is referred to as bond polarity. Bond polarity is simply, I have this atom of this element and I have this atom of this element. I don't care about all the other bonds there. Just between those two guys, are those electrons going to be shared equally or unequally? And that's what we use bond polarity to tell us. May not tell us that overall the molecule is polar or non-polar, but it can tell us just between those two guys, is that bond going to share those electrons equally or unequally? So the three sort of types of bonding that we talked about up until this point, you could kind of illustrate here. On one end of the extreme, we have an ionic bond, which is always between a metal and a non-metal, where we do get that transfer of electrons from the metal to the non-metal. We create that cation, which is positively charged, or anion, which is negatively charged. Again, that is what is holding that together. No sharing of electrons. On really the other end of the extreme, we have a non-polar covalent bond, which is always between two nonmetals. And we have equal sharing of electrons. like we saw with H2 or F2. And sort of in the middle between them, we have a polar covalent bond, or just a polar bond, also between two nonmetals. And here we have unequal sharing of electrons. And right there is our example there. Obviously, HF is an example of that. So one end of the extreme with ionic bonds, with metals and nonmetals, off goes the electrons completely. Somebody completely loses electrons. Somebody completely gains electrons. Other end of the extreme, nonpolar covalent bond, we have like nobody's losing electrons, and we're going to be nice to each other and share the electrons perfectly equally with each other. And in the middle, we have not such an extreme that we give away the electrons completely, but not such a happy situation where we're going to share them equally. We have some degree of sharing happening, but it definitely is unequal sharing, but not such unequal sharing that the electrons actually move from one place to the next. They're still hanging on and actually sharing. Any questions on the three different types of bonding there? Again, the two on the right are covalent and with two nonmetals and definitely sharing. Guy on the left there obviously is ionic and no sharing occurring. Any questions on that there? So you may be asking yourself, well, how do I know when I put like these two guys together, are they going to play nice and share equally? Or are they not going to play nice and share unequally? And it really, like I said before, is the electronegativity values that help you determine whether or not those electrons will be shared equally or unequally. So let's talk a little bit how we could use something like electronegativity to help us decide, are we going to get a polar bond or a non-polar bond? So electronegativity, as I mentioned, the ability of really an atom to bring electrons towards itself. It is related to some of those periodic trends. Electronegativity is related to electron affinity and ionization energy. Fluorine, which is upper right, has all those periodic trends that we talked about earlier that pretty much wants those electrons to come to itself, and it's not going to give away its electrons. To the left, where we find sodium, has all the really opposite stuff in terms of periodic trends. It's like, go ahead, take my electrons, you know, I don't care too much about it. So there was a guy named Pauling who did come up with actual values for electronegativity. And the general trend, as we talked about, up and to the right, it increases, left and down, it decreases. Pauling came up with the idea of giving values to the elements of 0 basically to 4. 4 is the most electronegative. And 0, not so much, really not so much. I'll just write that, why not? Not so much. Yeah. So 0, pretty much no electronegativity, is not really interested in gaining electrons, and 4 is the most. Fluorine has a value of 4, as we'll see here in a second. We could actually use what is sometimes referred to and calculated as the difference in electronegativity values. Delta En, delta is change, En is electronegativity. And that's basically taking the two elements that are involved in the bond and you subtract their electronegativity values. And if you subtract their electronegativity values and you get a value from like 0 to 0.4, that is considered a nonpolar bond. If you subtract the two electronegativity values, I'll go this way up, and you get above 0.4, like 0.5 to below 2, that is considered a polar bond. And typically, if you go above 2 when you subtract, that is an ionic bond. So 0 to 0.4 is considered a nonpolar bond. By the way, if you get like a difference in electronegativity of exactly 0, that is also sometimes referred to as a pure covalent bond, which is still a nonpolar bond. So it's still a nonpolar bond. It just means that it has exactly perfect sharing of electrons. So these sort of cutoffs helps us decide when we look at an electronegativity table, what we would expect. Do you need really the electronegativity table to help you with ionic bond? The answer is no. All you need to know is that's a metal, that's a non-metal, that's an ionic bond. You don't really actually need the values to help you do that. In a lot of cases, you could actually use the general trend for electronegativity to help you figure it out. And we'll see some examples here in just a second. So let's take a look at electronegativity table. Here's one. And you can see the values increases as we go up here to the right. Here's another one. Here's another one. I'm going to go with this one. There's a lot of numbers on that one, I think. All right. So obviously these values would be provided for you. Actually, we'll go back to this one here so you can see a little. So for example, let's take a look at the ones that we saw earlier. Earlier, we looked at sodium chloride. So if I wanted this chart to help me determine if that's ionic, which by the way, again, you don't need the table. You should just know that's a metal and a non-metal. I would look at sodium, which is 0.9 on the table right there. I would look at chlorine, which is 3 on the table, and basically just take the larger number minus the smaller number. So the difference in electronegativity here will give me 3 minus 0.9. That gives me a 2.1 value. So remember that anything above 2 is ionic. So that is again why we get a transfer of electrons here. Is that rule perfect? It is not. You could find a combination of a metal and a non-metal where you'll get a difference less than 2, but it's still ionic. So that's why I said you really don't actually need the table for an ionic compound. Metal, non-metal is all you need. If you remember, we also looked at F2, which clearly if we look at F here, that is 4 and that is 4, which means when we take the difference here, that is going to be 4 minus 4, which is 0. Anything from 0 to 0.4 is non-polar. So that tells us it's non-polar. The other one that we looked at was H and F, right? H is 2.1, F is 4. So when we do the difference in electronegativity, that is 4 minus 2.1. That's going to give us a 1.9 in this case. 1.9 falls in that category of like 0.5 to just below 2, pretty close to 2, just below 2 there, which means it's going to be a polar bond. Also illustrates that between hydrogen and fluorine, it's almost to the point where it's going to transfer those electrons. Hydrogen is like barely hanging on in this case, but there is still some aspect of sharing. Question on how to use this table. Why don't we try some here and see what you come up with. Yeah. In this case, where you're doing difference in electronegativity, you just want to get a positive number. So take the larger number minus the small number. It's the best way to do it, yeah. It's really the difference that's important, not really the negative or positive part of it, yeah. Other questions on that? Okay, so let's take a look at one. We'll go to this guy here. All right, so you do it here. You decide, is it polar, non-polar, or ionic? If we put together, let's go with carbon and oxygen. We'll do sulfur and oxygen. Why don't we do, let's do potassium and bromide. Let's do carbon and hydrogen. And let's do carbon and sulfur. So again, start with that one up there, which is potassium, which would be 0.8. And our bromine, which would be 2.8. And again, our difference in electronegativity will give us 2.8 minus 0.8, which would give us 2. And we would know that it is ionic. And like I said, with the ionic sort of cutoff, if you will, it's really not 100% because you could definitely, like this one, it's right on 2. For example, if we took like, I don't know, sodium and phosphorus, for example, right? And put those guys together, we're going to be below 2. So it doesn't work perfectly for ionic. And that is why it's best to know when you see K, which is a metal, and Br, which is a non-metal. That's all you really need. You don't actually need the numbers for ionic, and it will be an ionic bond. So for ionic, really just stick with the metal, non-metal. You'll be in good shape. It doesn't perfectly work the two for all ionic bonds. We look at carbon and oxygen. Carbon is 2.5 up there. Oxygen is 3.5. Difference in electronegativity here gives us 3.5 minus 2.5, which looks like 1. Now that I fix this down here, 1 is obviously above 0.5 and below 2. So that is going to be a polar bond. The one that's more electronegative is the oxygen, which means if we were to draw that arrow, it would actually be pointing towards the oxygen side, which is more negative, and the carbon is more positive. Electrons are moving towards the oxygen in this case, still being shared, but moving that way. Sulfur there is 2.5. Oxygen again is 3.5. Actually, in that case, I guess the carbon. Yeah. And we are going to get a difference in electronegativity. Basically the same thing. We're going to get a difference of 1 when we subtract that. Also telling us that that is a polar bond as well. Again, here the oxygen being more electronegative. Carbon, which is 2.5. Hydrogen is 2.1. Difference in electronegativity here, 2.5 minus 2.1 gives us a 0.4. 0.4 is our cutoff here for nonpolar. And this bond right here is really why the cutoff is 0.4. Carbon hydrogen bond, as we'll talk about when we get to organic chemistry, is pretty much the basis of all organic molecules, and they're pretty much nonpolar. So the carbon hydrogen bond is technically speaking nonpolar, technically speaking sharing the electrons equally between them. No arrow would be drawn on this one because there is no negative side or positive side. Again, neutral if you want to think about it that way, no real overall charge sort of happening. Question on that one there. If we look at carbon here, which is 2.5, sulfur, which is 2.5, that gives us a difference in electronegativity of 0, I hope, when you subtract both of those numbers. And in this case, that would mean that this is actually a nonpolar bond as well. So this illustrates a really good example. You can technically have two guys that are different elements and still able to share the electrons equally. By the way, that difference of 0, it means it's really a pure covalent bond, which is still a nonpolar bond. It's like your perfect equal sharing of electrons. You may say to yourself, but they are different elements. How does that work? There is a relationship. If you look at this table, which is sometimes referred to as the diagonal relationship, carbon and sulfur are diagonal of each other on the periodic table. Carbon's further up, sulfur is further to the right. They cancel out their differences and they end up with the same electronegativity value. You also see that in a couple other places, nitrogen and chlorine. If you look at nitrogen and chlorine, they have the same diagonal relationship. And you will run into that occasionally where one's further up and one's further to the right. They essentially will cancel out their differences. Question on how to use this. Now, if you needed these numbers, they would be provided for you. There are a lot of situations where you could just use the general trend and be in good shape. 100% of the time, if the things are in the same row, you don't even need the numbers, you just need to know the trend. So for example, the one that we did previously up here, which is carbon and oxygen. Here is carbon, here is oxygen. They're in the same row on the periodic table, which means oxygen is further to the right, which means it should be more electronegative, which means that's all you need to know. And that's probably going to be a polar bond. And you can make a pretty safe assumption on that. You actually don't even need the numbers. If you look at sulfur and oxygen, sulfur is here, oxygen is here. They're in the same group on the periodic table. Electronegativity increases as you go up a group, which means you can make a pretty safe bet that oxygen should be more electronegative than sulfur. And you can also make a pretty safe bet that it is going to be a polar bond. So a lot of cases you can run with just the general up and to the right is more electronegative, that general trend, and make a pretty safe assumption as to whether or not you will have a polar bond or a non-polar bond. Occasionally you just got to watch that kind of diagonal relationship, but in most cases, you could just use the general trend especially if they're in the same row. You definitely could use the general trend, and if they're in the same group, you could use the general trend without needing the numbers. Again, whichever one's further up and to the right should be more electronegative and should result in a polar bond. Any questions on that there? No. Okay. So obviously, as we saw there, atoms with really differences in electronegativity, like when we have metals and nonmetals come together, does result really in an ionic bond, and that's when we get that complete transfer of electrons. Obviously, everybody kind of sandwiched up there in the nonmetal region where they have very similar electronegativities. They're just going to agree upon sharing those electrons. We're not going to get that transfer that occurs. So you'll have some type of covalent bond that will be there, either nonpolar or polar. Here's what I think from your book, the cutoffs and all that good stuff are similar to in your book. So as you can see, it's not perfect that sort of above 2 or 2 and above for ionic. Now that we understand the different types of bonding, now that we understand how we can determine if we're going to share electrons equally, let's talk about the proper steps that you should follow when you're drawing Lewis structures for covalent compounds. These are nonmetals that are going to be sharing electrons. If you follow these steps, you should end up with the right structure, or a pretty good structure. I'll put it that way. That's a better way, probably. If you decide to do what a lot of people want to do, which is a really bad idea, I call it piecework, where they go, okay, I'm going to draw the dot structure for this guy. I'm going to draw a dot structure for this guy and all their dots, and you try to figure out where all the dots go. You're going to screw up. You're going to end up with the wrong number of bonds, not enough electrons. So if you follow these steps, you should really end up with a pretty good picture when it's all said and done. So let's talk about those steps. First off, you want to think about sort of a logical arrangement of how to put everybody together. So there are some common things that help you decide that. Typically in the center atom is the least electronegative atom. So we want the least electronegative guy in the center. And in a lot of cases, everybody else is like attached directly to him. Yeah, so there's usually like a guy in the center. Everybody else is sort of attached to him. There are places where there's other things attached, but a lot of stuff that we deal with in this class will be like one guy in the middle, everybody else sort of attached to it. We should never find fluorine in the middle because it is obviously the most electronegative. We should obviously not find hydrogen in the middle because that will make it have way more than 2 bonds and 2 electrons, and it should not have that either. Probably the most important thing that you do is the second thing there, which is you need to count up the total number of valence electrons that you need to draw. That number is super important because when you are done with your picture, you got to hit that number exactly. Now, if we are drawing something of a polyatomic ion that has a charge, you do need to take the charge into account. So if you got something that is positively charged, it has lost electrons. So you need to subtract that from the total. If you have something that is negatively charged, you need to add that to your total. Otherwise, you're going to end up with like one lonely electron, and that's not good for us. It can happen in real life, but for us, it should not happen. So you should be good. Everybody should be happy and paired off and all that good stuff. Once you have sort of the logical arrangement in your head, you got like the total number of electrons you got to put in your picture. What you want to do is go from the center atom to each of the outside atoms and make one single bond. Personally, I use lines, so make one line to each of the outside guys. Each line represents 2 electrons, so you want to count up how many electrons you just used. You want to subtract that from your total that you calculated in number 2. And all the remaining electrons should go on the outside atoms in pairs, dots, pairs, until everybody hits 8 on the outside, except for hydrogen. You're going to go all the way around until you fill up all the outside atoms with electrons. Now, you may get to a point where you fill up all the outside atoms and you still have electrons to go. At that point, you then go to the center atom and you put those electrons on in pair. For our purposes, you should be done at that point after you fill up the center guy if you need to. Once you've distributed all your electrons, you want to make sure that everybody has met the octet rule, which means everybody has 8 electrons, be it dots or lines around them, total of 8, except for obviously hydrogen, this should only have 2. If you find that somebody does not have 8, that is when you should lay up a double bond and to try to fix it. And if the double bond doesn't work, then you need to move to a triple bond to try to fix it. You should not double bond or triple bond out of the box. Bad idea. Be a bad structure. So you want to kind of save double bonding and triple bonding to sort of fix a problem where somebody does not reach the octet rule. That's a lot of words. Let's go through ones together here to see that and put it in you know, whatever I'm trying to say there. All right, NF3 here. So the first thing that we want to do is calculate the total number of valence electrons. So nitrogen is group number 5, which means it should have 5 valence electrons. There are 3 fluorines. Each fluorine is group 7, which means it should have 7 valence electrons. That is 21 and 5. That's 26 valence electrons. That number is super important because when our picture is done, that is exactly the number of electrons our picture needs to have if we did it correctly. All right, so we got nitrogen and fluorine here. Logic tells us that if we have 1 atom of an element and like 3 of another, the 1 is usually in the middle, but we could verify that nitrogen is less electronegative than fluorine. So nitrogen should be in the middle. So our logical arrangement would be nitrogen in the middle. We would lay up a fluorine on each side, maybe one below. The question that maybe someone's going to ask right now is, can I put the fluorine on top? The answer is yes, you could. You could not put it on the bottom. You could put it on the top. I got my logical arrangement. I got my total number of valence electrons. We're going to make a single bond to each of the outside bond atoms in this case. That has now used how many electrons? Each line represents 2, so that's 2, 4, and 6 electrons. We want to subtract that off from our total there. We have 20 more electrons that we need to put on the picture here. Those are going to go on the outside ones in pairs until it hits 8. So 2, 4, 6. That fluorine is now full. 8, 10, 12. That fluorine is now full. 14, 16, 18. That fluorine is now full. I have now distributed on my picture a grand total of 24 electrons. I still have 2 more to go. I am done with the outside ones. Now I go to the center, also goes on as a pair of dots. I have now put on my picture a grand total of 26 electrons, which is good. The last thing that we want to check is to make sure that everybody has hit the magic 8 number there. Looking at our fluorine there on the right, it has 2 electrons, 4, 6, and 8 electrons. Every single fluorine is identical, so they all have 8. Our nitrogen has 2, 4, 6, and 8 electrons. Also has 8. It is, that would be our correct picture here without all the blue scribble. Looks something like this. Question on that particular one there. Yes. So that is sort of how you want to do it. You want to follow sort of those steps. It will lead you to the correct structure. Let's take a look at another one here. We'll do NO3 minus. So let's do this one together as well. Nitrogen has 5 valence electrons. There are 3 oxygens, which is group 6. And in this case, it has a -1 charge, which means I should add or subtract electrons in this case. We should add. Negative means that it gained electrons. So we would want to add 1 more to our total for the negative charge. That is 18, 19, and 4, 24, I think. Again, here, 24 electrons is what we need to draw. Again, here, just logically speaking, I got 1 nitrogen, 3 oxygens. Even without thinking about electronegativity, probably the nitrogen should be in the middle. And it should be nitrogen is to the left of oxygen on the periodic table, which means oxygen is more electronegative. So same arrangement here. Nitrogen, oxygen, oxygen, oxygen. Same idea. You can put the oxygen on the bottom if you want. We're going to follow the same step. I'm going to make a single bond. That is 2, 4, and 6 electrons, right? It's a lot of math at this late, but that's like 18 more to go, I hope, at this point, is what we should have left. So we just kind of subtract 6 there. We're going to put those on the outside first. So that is 2, 4, 6, 8, 10, 12, 14, 16, and 18 at this point. I have now put 24 electrons on my picture here. Is everybody good? Which one is not good? It is the nitrogen. All the oxygens, if you go around, all have 8 electrons. The nitrogen in the middle only has 6. So this is the point where we need to fix it. Can I just lay up a couple of electrons there? I cannot, because now I have 26, which violates how many electrons I should have. So this is the point where we want to fix it by making a double bond. Can I just throw a line here? Same reason I'm now at 26. The oxygen up there on top has way too many electrons. So what we want to do in a situation like this is we're actually going to take a pair of electrons and bring them in to do the double bond. And if we do that, we will end up with a double bond up on top. And those guys will still remain single bonded over here. And if we count up our electrons, we actually still end up with 24 total electrons, which is what we want. The nitrogen in the middle now has 8 electrons, 2 to one single bond, 2 to another, and 4 for the double bond up on top gives it 8. The oxygen that's double bonded has the 4 dots and the 2 lines, which gives it 8, and each of the oxygens have 8 single bonded. We typically do put a bracket around it and the charge on the outside since it has a charge when you draw a Lewis structure for it. Question on that there. So yeah.
I know we did the double line, but can we do it on the right or left?
Yeah, so that's a good question. You absolutely could in this case. Each of the oxygens are identical to each other. So if we took the electrons from the left there and brought them in, you would end up with a picture that looks like this. And as your question, you could also brought in instead of those electrons on the right, and you would end up with a double bond that looks like this. And obviously everybody else would still be single bonded. And all 3 of these structures are actually related to each other. They're what are known, and sometimes you'll see this 2-headed arrow. They are what are known as resonance structures. And resonance structures basically occur in this situation where you have more than one option where you could do the double bond. Because we have more than one option where we could do the double bond, we could draw 3 different structures, which they all are basically equivalent to each other. They're all basically the same. And if you're not asked to draw a resonance structure, you could draw any one of those 3 and it would all be correct. If you're asked to draw resonance structures, you would do all 3 in this case. The reason for that is when we bring in those electrons, those sort of double bond electrons, they're what are referred to as being delocalized, which means in if I just draw everybody kind of single bonded, those double bonded electrons in some cases may be over here at the top oxygen, but then they'll kind of move over to the right oxygen and they may move over to the left oxygen. So they're sort of bouncing around from each of the oxygens, and the real structure is probably somewhere between all 3 of them because those double bond electrons can kind of move around freely, if you will, and kind of go from one oxygen to the next. So that usually occurs whenever you have a situation where you have an option of more than one double bond or where you can put the double bond. Question? Or, yeah. Resonance structure? Yeah. Other questions on that there? All right, let's try some here maybe. Actually, why don't you draw? Let's see. Let's do SH2. Let's do NH4 plus. Let's do SO2. Let's do why don't we do the one that was on the page, CO3 2 minus? Why not? And while we're at it, why don't you do N2? All right, take a couple minutes here and see what you get. Look at some of these since we're getting to the end here, just to kind of make sure, hopefully you're at least starting on the right page. So we'll add up our valence electrons here for SH2. So that is 6 for the sulfur, 1 for the hydrogen. There's 2 of them, which means 8 valence electrons. Clearly hydrogen cannot be in the middle, so sulfur needs to go in the middle. We're going to put our hydrogens on the outside. We're going to do the same process, 1 bond to each hydrogen. That is 4 electrons, which gives us 4 more to go. Do I put dots on the hydrogen? I do not. That is done, right? So both of the hydrogens are full, which means I need to go to the center atom and put 2 and 4 dots there. That then gives me the sulfur in the middle that has 8, which is good. And each hydrogen has 2, which is exactly what it should have. And that would be a winner right there. Yeah. Any questions on that one there? Okay. Doing the same thing here with our nitrogen. That is 5 for the nitrogen. There are 4 hydrogens each at 1. The plus charge here means I should add or subtract. Plus means that we lost electrons. So we do need to subtract 1 for the charge there. That's going to give me 9 minus 1, which is 8 valence electrons as well. Again, hydrogen cannot be in the middle, so we got to go with our nitrogen in the middle, a hydrogen around. And a single bond to each hydrogen gives us 2, 4, 6, and 8, which is good because now we're out of electrons. Every hydrogen has 2, which is good. Nitrogen in the middle has 2, 4, 6, 8, which is good. Again, put a little bracket to make it nice and pretty looking, right? And put a little plus on the outside, gives us that guy. Question on that one there. Going to our SO2, sulfur is 6, oxygen 2 times 6, that is 18 valence electrons. Between sulfur and oxygen, sulfur is less electronegative, so it should go in the center. Oxygen on the outsides, following our same path, single bond, which is 4 electrons. That leaves us 14 more to go. That's going to go on the outside in pairs. So 2, 4, 6, that is full. 8, 10, 12, that is full. At this point, I have put on 16 electrons. I have 2 more to go. Those 2 go where? They go to the center now, also as pairs. And that is how that gets there, not double bonded everywhere, by the way. That is how those electrons get there, and they should be there. At this point, though, when we look at the oxygen, they're all good. They have 8, but sulfur only has 6. So this is a point where we want to make a double bond. Doesn't matter which oxygen in this case I do it with. It doesn't. You can do it on either one. I'm going to take a pair of electrons, remember, and we're going to bring it in to do the double bond. So we will end up with a double bond sulfur there, still the dots. Oops. Now when we look at it, each oxygen still has 8. The sulfur by double bonding also has 8. 4 with the double bond, 2 with the single bond, and 2 with the dots, right? Gives us 8. We could have drew the other one, which would have been a resonance structure if we just drew the double bond on the other side. Again, either one of those pictures would have been perfectly fine in this particular case. Question on that one there. Coming down here to CO3 minus, carbon is 4. 3 oxygens at 6 each. Minus 2 means I'm going to add 2 to my total. That is, what we got there, 24? No, 18, 20, 24. Yep, there you go. In the middle here should go carbon, which is less electronegative than oxygen. Carbon, oxygen around. We're going to do, again, a single bond to each of those. That is 2, 4, and 6 electrons. That leaves us 18 more to go. So we're going to fill up the outside, 2, 4, 6, 8, 10, 12, 14, 16. There we go. 18, I think, right? At this point, we have now filled 24 electrons. Is everybody good here? Carbon is not good. So we have an option of 3 places to make the double bond. So again, I'll go with the top here, going to bring it in. And we will end up with that double bond up on top. And again, we want to put a little bracket and a -2. Just like the other one, we could have double bonded to the right, which would have gave us a perfectly fine structure. We could have double bonded to the left, which would have gave us a good structure. Those also would have been resonance structures of each other. Question on that one there. All right, to finish up this last one, which is N2, that is 2 times 5, which is 10. There is really no center atom here. There's just two, which means we actually just put them side by side. We actually follow the exact same process here. We're going to do a single bond, which is 2 electrons. That means I have 8 more to go. We'll do the same process. We're going to pair up on the outside. So 2, 4, 6, and 8. At that point, I have now distributed all 10 electrons. Are both nitrogens good? They're not. So we want to try to fix it by making a double bond. So we're going to take a pair and move it in. When we do so, we now end up with a double bond that looks something like this. Did that fix our problem? Did not. Got us close. So at this point, we need to make a triple bond. Works the same way. You need to take another pair of electrons and bring them in. When you do so, you end up with now a triple bond and 2 dots on each of those nitrogen. And now they have 8 each. So when we redraw it, maybe here. So it ends up being like this guy here, right there. Go that way. With our triple bond in the middle and our lone pairs on each of the nitrogen, giving them each 8. Question on how to draw Lewis structures. So if you follow those sort of steps, you should end up with a pretty good structure. Key things: don't double bond and triple bond out of the box, and total number of electrons and distribute them. All right, a couple of reminders. 1 week from today is our first exam. Yes, covering chapters 1 through 4. It will be taken during lecture time, the entire period. There will be no lecture, obviously, on that day. It will be part multiple choice, I think, and part work out the problem like I put it in the announcement. Also a reminder, right, the online homework should be due sometime next week as well. So hopefully you've been working on those. Don't wait till the last minute. It will not be extended, yes? All right, have a good lab if you're off the lab.